Okay, let's talk about this logistic differential equation. Okay, so it's dp, the rate of change of the population with respect to time is kp. Note that up to there it's exactly the same as the regular population growth model, but it's multiplied by 1 minus p over k, where we call the k carrying capacity. Carrying capacity. Okay, so this name is a very logical name. I'll explain why. So let's think about a little bit more realistically how population grows. Right? So it is a reasonable assumption that the more people you have, the faster the population will grow. But after a certain point, if there's too many people, we will have to compete each other for food, resources. So then some people will lose out, so it'll start shrinking, right? It'll start shrinking, and depending on the economy, depending on the how much resource the country has, right? There will be, so we're assuming there will be some value, right, where the population is comfortable to stay around or can support a certain amount of population. Okay, so it'll increase. As it gets too big, it'll eventually have to plateau out, right? And if it goes over this, right, it'll actually, so in real life there will be shocks to go over this, even so there'll be more people than actually that the country is able to carry. It'll start heading back down. Now this equation explains that concisely. So let's see what happens if the population is greater than the carrying capacity. Then we get p over k, divide both sides by k, you get greater than 1, which means 1 minus p over k is negative, which turns the dp over dt to be negative, which means the population is decreasing. So if the population is over the carrying capacity, you'll have to come back down. That's what it's saying basically. And if the population is less than k, the reverse will happen, right? The dp over dt will still increase. So that's why it's constantly going up all the way up to the carrying capacity. Now, more interesting thing is if you actually make p really small, okay, really small. So really small is really relative here. If the population carrying capacity is like 2 million, really small will be, maybe 1,000. So we're referring to like this part of the graph here. Okay, so this part of the graph, it looks like a normal exponential function, right? After that, it starts to behave oddly and then starts plateauing out and doesn't look like an exponential function. But if p is really small, right? So let's say p is of course less than k, but it's really small. Essentially, p over k will be approximately 0. Okay, then the dp over dt, which is kp 1 minus p over k. So if this is approaching 0, this actually becomes kp. See how it matches with the picture? If it's really small, it's essentially an exponential growth. Okay, and we call the y value, the population values of k, okay, and the 0 value, okay, I should actually have that time here, right? We call when the population is k or 0, we call this the equilibrium solution. Okay, so we call that equilibrium solution because let's say if the population is 0, it will want to stay at 0 because if there's no population, there's no growth, right? If population does reach k, because of the resource situation, it will want to stay at k. Okay, it wouldn't want to decrease or you wouldn't want to increase either. Okay, so they both, if the population does reach at either levels, they will want to stay there instead of going up or below. So we call that an equilibrium solution. If certain things, instead of if it reaches a particular point, if it wants to stay there, okay, instead of increasing or decreasing.